Okay, welcome back once again. Hope you're enjoying the sessions. This is Chemistry 3202 Course Overview Review. What we'll be looking at today is a substantial lesson here. Very important lesson because there's always one of these questions on the long answer part of the final exam. And what this lesson is, of course, is Section 3, Lesson 2 of ice tables. Here we go. Okay, here's the textbook references to this section if you want to do some background reading on this. And there's a few questions there in the textbook that pertain to what we're doing. So have a look. If you need any help, you might want to ask the online tutor to help you out with one of these questions. Or if you want to leave a note in the discussions, I can do one or two of these problems for you as a recording. One of the things we want to keep in mind as we do these ice table equilibrium calculations is this little business that we learned last day about what K represents. Remember, K represents the numerical value of which side the equilibrium is favoring, right? Where is it lying? Is it lying to the product side, in which case K is going to be greater than 1. Remember now the greater than sign means the equilibrium favors that direction, so we're going to get more products than reactants. And in the other fashion here, if K is less than 1, then of course the reactants are going to be favored, and of course the equilibrium is going to lie in that direction. So let's have a look at some of these ice table questions and see what we can get out of this. Okay, here's the outcomes for this section. Some of these calculations definitely going to drive you crazy, but I guess with all of these types of questions, once you get it and understand what's happening there, no matter what we throw at you, it's kind of all the same. So there's 2 or 3 different sets of types of questions here, and once you get them, you'll find that they're pretty straightforward. But again, it's practice. Do a few problems, see if you can get it on your own, try it. If you don't try it, then you're going to find these very difficult. But give it a try and see if we can't straighten out that baby's face. There we go. Okay, what we're looking at is something called an ice table. And ice table, 1 second here now. Okay, ice tables. An ice table is simply a way of organizing the information that's given, and it's a way of organizing the mathematical information so that we can figure out the equilibrium values and therefore be able to calculate the K value or use K in the equilibrium expression to find some other value. So the letters in the ICE table, ICE, stand for the initial concentrations, the change in concentrations, and the change in concentration is always going to be based on the mole ratio from the balanced equation. And we're going to do that in an attempt to try and figure out the equilibrium concentrations. And once we figure out the equilibrium concentrations, we got the job done. We ever use K values then to figure out some value that we're trying to calculate. So here we go. 1 second here. Now what am I trying to do? Hold on now. I'll find them. Okay, there we go. Vanilla ice with a little ice baby. So let's make a little bit of ice of our own, I guess, and see if we can't do a couple of these problems and make some sense with these ice table problems. So here we go. Okay, the very first sample we're looking at here, it says an equilibrium was established after 0.1 moles of hydrogen gas and 0.1 moles of iodine gas were added to an empty 1 liter reaction vessel and heated to 700 kelvins. All right, that's about close to 500 degrees Celsius, pretty hot. It says the color intensity of the mixture changed from deep purple to a lighter purple, and the change in color indicates to us now that that the equilibrium has shifted. All right, the color change tells us that we were once at a nice happy place, right? There was the color was constant, and all of a sudden we increased the temperature. The equilibrium now shifted, and now it's a lighter color, which means now it's reached this new equilibrium, and it's held at 700 degrees Celsius, so the color should no longer change after a period of time. They did an analysis of this new equilibrium mixture, and they found out that the concentration of iodine at equilibrium was 0.0213 moles per liter. Now there's a couple of things you got to watch out for in these problems. An ice table is based on initial concentration, the change in concentration, and the equilibrium concentrations. Everything is based on concentrations. The values that were given to us in this problem were quantities in terms of moles. So the very first thing we're going to have to do here is calculate the moles per liter, the concentration of the hydrogen and the concentration of the iodine. And in order to do that, we simply say C equals N over V for hydrogen. So C equals N over V is 0.1 moles divided by 1 liter container, and it works out to be 0.1 moles per liter. Now you got to watch this because sometimes they give you an odd size container. They might say you've got 0.1 moles per liter in a 2 liter container. I know some of you guys are saying, well, why did you have to do that calculation? The number really didn't change. But the reason we do that is to just make sure that the size of the container, like they might say a 3 liter container or a 4 liter container. So you really got to watch that with these calculations. Okay, we'll go down through now and we'll set up our ice table. So there we go. We've got a little table set up with ice there. Now you don't have to do a table as such, but you make sure you have ICE here. And our very first concentration of hydrogen, we just calculated it over here. Initially, this is what we put in the container. We put 0.1 moles per liter of hydrogen. So I'm going to fill out my ice table. Bang, 0.1 moles per liter of hydrogen. The exact same concentration of iodine was added, right? I don't have to do this calculation twice here, right? It's the same number of moles, it's the same volume, so the concentration should be the same for iodine. So we put it there. Now the interesting thing about this particular reaction is that we did not put any hydrogen iodide in the flask. Zero, nada, nothing. We didn't put anything in there. So when we look at this particular reaction, as soon as we put some hydrogen and iodine in this flask and put the cover on, almost instantly we're going to start getting collisions between hydrogen and iodine, and we're going to start seeing the reaction shifting in the forward direction. It's got to. It can't go backwards at the initial point because there are no hydrogen iodine in the bottle to go start reversing. So this reaction instantly is going to start moving forward. So what we need to be able to do is be able to calculate some kind of change. So they have to always give us some other tidbit of information here to be able to calculate everything else. And the information that they're giving us here is the fact that they measured the equilibrium value of hydrogen iodide and found it to be 0.0213. So what they're telling us is this value, not that one. Let me cover that up again. The value that they found was the iodine, sorry. So the iodine at equilibrium was found to be 0.0213. So we're looking at this value and saying, this is what we started with for iodine. This is what we ended up with. Can we calculate the amount of change in iodine? And the answer to that is absolutely, because the change in iodine is simply going to be the difference between the initial concentration of iodine and the equilibrium concentration of iodine. So we'll subtract those two values, and lo and behold, we get 0.0787. So I'm going to pop that value in my ice table. There we go. Bang. So we're saying that the iodine went down by 0.0787 moles per liter. Good enough. Okay, now what we want to do is, now that we have the change in iodine, we should be able to calculate the change in the other two, because the change is based on the mole ratio. And because we have a balanced equation, we should be able to figure out the amount of hydrogen that was going to be consumed. Because if this reaction is going to move forward and this much iodine was used up, it's a 1-to-1 ratio, so the same amount of hydrogen had to be consumed as well. Okay, so the other changes are going to be determined by the mole ratio. So in this particular example, the change in hydrogen is equal to a 1-to-1 ratio times the change of iodine. So hydrogen would be the same as the amount of iodine that changed. So we'll put that value in our table. So that guy went down. The negative sign means it went down by 0.0787. It decreased. And now that we have this value put in here, now we can figure out the equilibrium value for hydrogen. Should be easy enough to do. Okay, we just subtract those two, and there we go, 0.0213. Now we should also be able to find the change of hydrogen iodide based on this value as well, because for every 1 iodine, this guy is going to go up by 2. It's going to be twice as much. So when we look at the change in hydrogen iodide, the change in hydrogen iodide is going to be twice as much, or a 2-to-1 ratio, required over given, 2 to 1 times the iodine change. So it's going to be 2 times 0.0787, which equals 0.1574. There we go. Now this guy had to go up because initially it didn't start with any, so obviously it had to go up, right? It started with nothing. The reaction's definitely going to push forward initially. So this guy goes up by 0.1574, which now means we should be able to get our equilibrium value for the hydrogen iodide. And there we go. It's 0.1574. What we do here now is the question is done because they asked us to simply calculate the equilibrium concentrations. What I'm going to do here now is I'm just going to continue on and calculate K. So now that we have the equilibrium values, we should be able to calculate K. And K is simply based on the products over the reactants. That's what we've done in the last lesson. So in this particular reaction, we can see that hydrogen iodide squared, that's where the squared comes from because there's a 2 in front of the hydrogen iodide. So the hydrogen iodide squared divided by the reactants, which are hydrogen times iodine. There's a 1 over these guys because that's from the balanced equation. We put our values in and we solve for K. And lo and behold, K works out to be 54.6. Now, what we have to ask ourselves is what is the meaning of 54.6? Now, we also said before that as K is greater than 1, which it is here, K is 54, which is much greater than 1, we're saying that the reactants are going to be consumed more so, and we're going to produce more products. So we're pointing to the product side because K is greater than 1. Therefore, the products are going to be favored. And we have to say, well, does this make any sense to us whatsoever? Are the products favored? We look at the values. Indeed. Look, 0.15 for the products here. These guys are only 0.2. Right? So we're almost 7 times more products than we have reactants. So this is making sense to us, or it should, that the products have been favored. So what we're saying then is at equilibrium, the product concentration should be higher than the reactants. And the larger the K, the more the products are favored. So that's what we're seeing here. Let's look at another one. Okay, here's another type of chemical reaction involving an equilibrium reaction involving a ice table. In this particular reaction, we're saying we've got a 1-liter vessel again. We're putting 0.2 moles of nitrogen gas and 0.2 moles of oxygen. And we're going to bump the temperature up to 773 kelvins. And this time they're giving us information by saying that this reaction is going to go ahead 12.5% of the times. So of every single collision that goes on, the successful ones only happen 12% of the time. So we want to be able to calculate the equilibrium concentrations of all 3 species, and then I'm going to continue on to calculate K. So the very first thing we need to do, of course, is set up our ice table, because anytime we want to calculate K, it has to be based on equilibrium. Anytime they give us initials or changes or anything like that, that's our cue that we have to do an ice table. The very first thing we need to do is calculate our concentrations, because these values in the ice table are based on concentrations. So in this case, C equals N over V. The number of moles given was 0.2, and the volume of the vessel was 1 liter. So we can see that the concentration of nitrogen was 0.2, Coincidentally enough, they give us the exact same amount of oxygen. All right. Sometimes they don't do that. Sometimes they'll give us different volumes and different moles, in which case you'd have to calculate the concentration for each. So here we go. We've got the concentration of nitrogen initially. That's how much we put in the flask. And we also have the concentration of oxygen. Now, they didn't tell us how much nitrogen monoxide was in the flask, and the reason for that was because they didn't put any in. That's 0. Now, this question, remember I said before, they always give us something so that we can get a change. If we can get one change, then we can get all of the others. So this question is saying that the reaction will move forward 12% of the time. So if I gave you 100 molecules of oxygen here, only 12.5 out of 100 would move forward. So what we need to do is say, well, what's going to be 12% of 0.2 moles per liter? So that's what we're going to do. We're going to calculate the change here of the nitrogen or the oxygen, doesn't matter, either or. So in this case, we're saying the change in nitrogen is the percent reaction times the nitrogen initial. So we'll put our values in. And in this particular example, it's a percentage, so 12.5 divided by 100, that gets rid of the percent, times the initial concentration. So 12.5% of this is going to break down. We do our calculation here, and it works out to be 0.025 moles per liter change in nitrogen. So that's my change value for nitrogen. I can put it here. Nitrogen goes down by 12.5%. Now we can follow our logic here now. The fact that we have one change, now we can do a mole ratio to get all the other changes. Now the mole ratio for oxygen is easy enough because it's going to be a 1-to-1 ratio. It should be the same value. And we'll just calculate it here for you. Okay, and there we go. The change in oxygen is the same thing. It's a 1-to-1 ratio of the nitrogen. And this is from the mole equation. So it's going to be the same concentration. Okay, now if we want to figure out the change in the nitrogen monoxide, we can see that for every 1 nitrogen, we're going to produce twice as much NO. So the mole ratio is going to be 2/1, required over given. So it's going to be twice as much. So we can calculate that one. So the number of moles change, the moles per liter change of nitrogen monoxide is 2/1 times the nitrogen. And lo and behold, there we go. So we get 0.050. And I'll uncover that one. There we go. Now, calculating the equilibrium values should be easy enough because all we're going to do is subtract that value from that, subtract that from that, and then add those two together. So when we do this, we're simply going to complete our table now. So I'm going to subtract the first one. That's how much nitrogen, 0.175 moles per liter of nitrogen, is left in the bottle. Same thing is true for the oxygen. Now the NO is only going to be that little tiny amount there, isn't it? Because only 12% of this moved forward. So when we look at this, we're saying 12% moves forward. That means 88% doesn't want to go forward. 88% of these reactants prefer to stay as reactants. And that's why the values are so large here. So we can make a bold prediction here. We're saying that because this reaction has such a little tiny forward reaction percentage, it doesn't want to move forward. It prefers to stay on the reactant side. So what we're suggesting then is that K should be less than 1. We're predicting that the equilibrium favors this direction. K is going to be less than 1. Let's do the calculation and find out. Okay, so we're going to calculate this. Again, K is products over reactants, and in this case it's going to be the products NO squared divided by N2 times O2. We plug in our equilibrium values. There we go, 0.050 squared divided by 0.175 times 0.175. And the value we get out, remember we're predicting something less than 1. There we go. We get 0.0816. We put this in scientific notation. We'll move the decimal place 2 places. So that's -2. This value is indeed less than 1, as we predicted. So because it's going to be less than 1, we're expecting the products to be much smaller because the reaction only proceeds 12.5%. It only wants to move forward 12% of the time. The other 88%, it prefers to stay as reactants. So our calculations are making a little bit of sense. The numbers we're getting, we're able to make some kind of prediction as to whether it's going to be greater than or less than 1. There we go. Okay, here's another particular type of problem. Okay, in this one here it says an equilibrium was established in a 1 liter container again. 0.12 moles of phosphorus pentachloride was decomposed at 500 kelvins. At equilibrium, the concentration of chlorine gas was 0.0540. We want to calculate the equilibrium constant and state a conclusion. So that's what we've been doing all along. So the very first thing we want to do is make our ice table. And we're looking at this guy and we're saying, okay, we've got a 1 liter container. We've got 0.121 moles of phosphorus pentachloride gas put in this container. So that's our concentration, right? It's going to be 0.120 moles divided by 1 liter. We didn't put any PCl3 in. We did not put any chlorine in. The only thing that was put in this container was the phosphorus pentachloride. Remember, they always give us a piece of information to tell us, be able to calculate some kind of change here. And in this particular question, they're telling us the equilibrium concentration of chlorine gas. So we'll write that in down there, 0.0540 moles per liter. Now, we need to be able to fill this table out. Well, this should be easy enough for the most part. Okay, because we know that this guy started with no chlorine whatsoever. So if it ends up with 0.0540, that means the chlorine had to go up by that amount. So that was easy enough, 0.0540. And we're looking at this guy and we're saying, well, that's a 1-to-1 ratio. So if we started with nothing here, and if I get 1 mole of chlorine, then I should get 1 PCl3 as well. So if this guy went up by 0.054, this guy should go up by 0.054, the same amount, because it's a 1-to-1 ratio. There we go. So the change in PCl3 is a 1-to-1 ratio times the change in chlorine. So it's the same thing. The PCl5, it's also a 1 in front of this. So it's a 1-to-1-to-1 ratio. So if this guy went up by 0.054, then this guy should have went up by the same amount because it's a 1-to-1 ratio. Or sorry, down. Okay? This guy's going to go down by that amount because obviously in the beginning, this reaction has to move forward. So these guys went up by this amount. This guy had to go down by the same amount because it's a 1-to-1 ratio. There we go, 0.054. So we can easily figure out the equilibrium values here now. What I'm going to do here is simply subtract these two to get the equilibrium value. Right there, 0.066. And of course I'm going to add PCl3. There we go. Okay, now what we can do here is we need to calculate that's calculating the equilibrium value. Just done that. Okay, what we want to do now is calculate the equilibrium constant. So K is products over reactants. In this case, the products are the PCl3 and the chlorine gas. So PCl3 times chlorine gas divided by PCl5. We put in our equilibrium values because that's what K is based on, equilibrium values. That's the whole point of doing an ice table, to get the equilibrium values. And lo and behold, there we go. And when we work these guys out, it works out to be 0.04418. 3 significant digits here. So we would round the 8 up to a 2, and we get 10 to the negative 2. K is less than 1, so the reactants should be favored. Okay, reactants are favored. K is less than 1, so reactants are favored. There we go. Here's another problem. In this case, we're looking at another percent reaction. In this case, we're looking at 0.57 moles of carbon monoxide gas and 0.57 moles of water vapor are introduced into a 1 liter container, and then they're heated up to 600 Kelvin. And at that temperature, the reaction proceeds forward 82% of the time. All right, so what we're looking at then is that this reaction would proceed forward 82% of the time. We want to calculate the equilibrium constant and state a conclusion. All right. Well, the very first thing we need to do, of course, is calculate our concentrations. So C equals N over V for the carbon monoxide and the water vapor. Now, you got to be careful about water, because if this was in the liquid state, I wouldn't have to use it. So if this was a liquid right here, if water was a liquid, I'd simply box it out like that, and then I'd cross out that entire line. If it was a liquid, because remember, solids and liquids are not involved in any equilibrium whatsoever. We do not include them. Even though it's part of the chemical reaction, we would not bother to use it for equilibrium calculations. But in this case, because it's a gas, we have to use it. And we know what the concentration of the water gas is. It's 0.570 moles per liter. We didn't put any carbon dioxide in. We didn't put any hydrogen in this container. We want to be able to calculate a change of something, and that's why they gave us the 82.8%, because we know this reaction proceeds forward at 82%. So we can calculate the amount of change of the carbon monoxide by simply saying the change in carbon monoxide is equal to the percent reaction times its initial concentration. So there we go. We put these values in. So 82.8% or 0.828 times 0.570. This would be the change in carbon monoxide. We know that the change in water should be the same because it's a 1-to-1 ratio. If 1 carbon monoxide are used up, then there's going to be 1 mole of water used up. So that value should be the same. There we go. Okay. Now we also want to be able to calculate the carbon dioxide and the water, and we're saying, well, these guys should be the same as well, because they're all 1-to-1 ratios. So the only difference here, I guess, is that because the reaction's moving forward, there's none of this to start with, the reaction must be moving forward. If these guys go down, then this guy's going to have to go up by that amount. And again, it's a 1-to-1 ratio. Okay. The equilibrium values, we should be able to get all 4 of these values here now, because you're simply going to add these, and subtract these. That's what I'm doing right here, calculating the equilibrium values. Okay, so we'll subtract these guys right here, 0.098 for water. We subtract those 2 for water, 0.098. Carbon dioxide, we add those together, and hydrogen, we add those together. There's your equilibrium values. Now look at the size of them. These guys, 0.472, are much, much larger than 0.09. And the reason for that, of course, is this reaction pushes forward 82%. Only 8% of this stuff is left behind. The other 82% is pushed forward. So the products are much larger. So where we're predicting K to be greater than 1. Products are favored. So we go and proceed to calculate K. There we go. And again, if water was a liquid, we would not include water here, but because it's a gas, we have to include that in our equilibrium expression. Okay, we plug our values in, our equilibrium values, and of course the answer we get is 23.2, and K is greater than 1, so products are favored. That's what we predicted. Okay. Now we get into a situation here where what if we don't know what the change is? we want to make what's called a simplifying assumption. And this is going to come into play again when we do a unit on acids and bases. But sometimes we get questions popping up where we don't know what the change is, so we just assume that the change is an unknown and we call it x. And what we want to do is simplify the value of x and say, can we take it out of the equation for the most part? And what that is something called the 500 times rule, or the 5% rule. And this is dealt with on page 513 of your textbook if you want to do some background information on this. And the way we find, or we simplify, is we simply look at this and say, well, what's the ratio of the initial concentration divided by the equilibrium constant? All right. When you do that calculation, they'll give you an initial value and a K value. Do this little ratio, and what we say is that if this ratio turns out to be greater than 500, the x in our ICE table is going to be negligible. And what that means is that it should end up being insignificant when compared to the initial amount. And I'll do an example to show you what we're talking about here. In other words, we're saying it's insignificant. It's not big enough that when we subtract it, it's not going to be big enough to make any significant difference. All right? It's like having a millionaire who has a hole in his pocket and he loses 25 cents on the driveway. Is that 25 cents very significant? Not at all, right? Not to the millions that he's got in the bank. It is a loss, but it's not significant. Okay, x makes no difference. The other situation is if x is less than 500. Now, if if the ratio is less than 500, what we're saying here is that, wow, this is significant. If we're going to subtract a value that's unknown and it's going to be a significant value, then we better take it into account. We better not just ignore it as if it's not going to make a difference. So this is like the millionaire now who lost half his money in the stock market. You know, he's got $2 million, he's just lost $1 million. That's a significant loss. All right, so he's going to have to somehow take that into account. So that's what we're trying to do, is just trying to get a feel for how much the loss is. Is it a significant loss? If it is, we got a big calculation to do. If the loss is insignificant, then we can just ignore it. And here's what I'm talking about. If it's a significant loss, we would have to do the quadratic equation, and x would make a great big difference. X would be a big factor. And I'll show you an example now in a sec. Okay, so here we go. Here's an example involving the quadratic equation, or lack thereof. This is question number 15 on page 509 of your textbook. And what we're dealing with is we're going to put some hydrogen bromide in the container, and they tell us how much exactly they're going to give us. All right, they say we got 0.090 moles of HBr in a 2-liter flask. So the very first thing I want to be able to do here is be able to calculate the concentration that we put in that container. So the concentration of the hydrogen bromide is going to be 0.090 divided by a 2-liter flask here, and the initial concentration of HBr is going to be 0.054. So that's my initial value right there. Now that's all they tell us. They don't give us any more information to do this question. And remember what I said? I said they always give you something so that you can calculate a change. Well, in this case, they don't. They want you to try and figure it out. All right. So what they're saying is that I'm going to put some HBr in a bottle. There we go. I'm going to cap the bottle and let it go. So initially, I didn't put any hydrogen. I didn't put any bromine in here. None of that stuff was put in this bottle. So the reaction is definitely going to proceed forward. How much? We don't know. Well, let's call it X. If this reaction moves forward, it's going to go forward a certain amount. It's got to go forward. So if bromine goes up by a little bit, then hydrogen has to go up by a little bit. And if we look at the mole ratio for HBr, we can see that the hydrogen bromide is going to drop by twice as much as the hydrogen. It's a 2-to-1 ratio. So if the hydrogen went up by X, this guy is going to have to go down by 2X. Okay, now we've got a change related to all three of these species. So I would proceed here now to say, okay, well, what's the concentration of bromine? Well, it's going to be X at equilibrium. The concentration of hydrogen is going to be X at equilibrium. And the concentration of HBr, this guy's going to be a little more complicated. It's going to be 0.0545 minus 2X at equilibrium. Now this is what we're talking about. Is this drop, is X going to be big enough to be significant compared to the 0.045? So this is our millionaire right here. Is this loss only going to be 25 cents? Or is this loss going to be another $1 million? Is it significant? And the way we determine if this is significant, we look at the initial concentration and we divide it by our K value that's given. So we want to do our 500 times rule, and there we go. All right, now on the public exam, they're looking for you to state this. They want you to state, say, a simplifying assumption or write in the 500 times rule. And the ratio, the 500 times rule is simply saying the ratio of the initial concentration divided by our K. So there we go. That's my initial concentration. I'm going to divide it by my K value. And this works out to be 10,714,285.7. Well, that's quite much larger than 500. So what we're saying then is because it's greater than 500, this change is insignificant. It's a very, very, very tiny, tiny amount compared to the 0.045. So looking at this up here, we're saying this X is insignificant. Well, let's get rid of it. Let's just take this and cross it out. It's insignificant. It's not going to make any difference to my calculations whatsoever. Okay? So what we want to do now then is we want to go ahead and proceed to solve this problem. And we're going to say, okay, the value of K is going to be products over reactants. So hydrogen times bromine. Okay, I don't know what that is there, but let's just see if we can't fix that up a bit. Okay, there we go. So this is the hydrogen concentration at equilibrium times the bromine concentration at equilibrium divided by HBr squared. And remember where the squared comes from, right there. We'll put our values in this time. Now watch what happens. The value of K was given. It's 4.2 times 10 to the 9. This guy is X, and this guy is X. We don't know what they are at equilibrium. And look what we've done to our simplifying assumption down here. We've got rid of the minus 2x. Had we kept the minus 2x in down there, it would have ended up being something like this. 0.045 minus 2x squared, which would have been a quadratic equation. You would have had to work this out. That would have been 4x squared minus 4x times 0.09 something. Right? It would have been a quadratic equation, and that would have been quite ugly because we would have had to do a quadratic formula to solve it. But by getting rid of this right here, we've simplified it so we don't have to do the quadratic equation. And what we're going to do now is simply multiply these together. So that's going to give me x squared, and then I'll cross multiply. Right? Because that's like saying there's a 1 under here. So cross multiply. We're going to simplify this. So x squared is going to be 8.5 times 10 to the minus 12. Now we take the square root of that, and we end up getting 2.92 times 10 to the minus 6 moles per liter for x. Think about it now. The concentration of this guy is 2.92 times 10 to the minus 6. That's this number. 0.000000292. That's not very big. That's a very, very tiny number. Okay, does that make sense? Well, let's look at the value of K. K is 10 to the minus 9. K is so very, very tiny. K is much, 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 much less than 1, which means the equilibrium lies way, way, way to that side. It does not want to break down. Any breakdown represented by X is so very insignificant. It's not very much at all. All right? So we want to be able to validate our assumption here, and we're saying, okay, let's put in that value for X. Let's put in 2.92 times 10 to the minus 6 right here. So we put that value in, and we end up getting 0.0. When we subtract this, we end up getting 0.044994. Well, we only got 2 significant digits in this question. So with 2 significant digits, the 9 rounds up, and it ends up being 0.045. Sure, that's exactly what we started with. That's what we mean by being insignificant. Yes, there is a change, but the change is so subtle, it makes no difference to what we started with. And the reason being is because K is so tiny. There we go. Let's try another one. Okay, here's another problem. This is number 25 on page 515 of your textbook. The only thing that's given is the value of K. Look how tiny that is. 10 to the minus 8. That's very, very tiny. This reaction will not or does not want to go forward. What's given? Okay, they gave us the initial concentration of the cobalt chloride. We didn't put any COCl2, it's not cobalt chloride, my mistake. That's an oxygen, that's not cobalt. So carbon, oxygen, and chlorine. And the concentration of carbon monoxide is nothing. We didn't put any in the flask. The concentration of chlorine should be nothing. We didn't put anything in the flask there either. So the only thing that was given was the fact that the initial concentration of the COCl2 was 1.5 mole per liter. And that's all that's given. So we're saying, okay, fine. We don't know any change. So that in itself tells us that we're going to have to do a simplifying assumption. Because we don't know what the change is, we'll say, well, it has to be something. So let's say it goes up by X. Well, if chlorine goes up by X, then the carbon monoxide goes up by X. Which means, looking at this 1-to-1 ratio business, if these guys all went up by X, this guy should have went down by the same amount. Because it's a 1-to-1 ratio. Okay, a little bit ahead of myself here now. The equilibrium values, well, for chlorine, it's going to be X. For carbon monoxide, it's going to be X. And for COCl2, it's going to be 1.5 minus X. Now, the question comes up. Is this going to make a difference to the 1.5? Here's your millionaire once again. Is this loss going to be a few pennies, or is this loss going to be $1 million? Is it significant? So what we have to do is say, let's do our simplifying assumption. We do the 500 times rule, and as I said, on the public exam, they're going to be looking for you to state that you're doing a simplifying assumption here. We do our simplifying assumption by simply saying it's the ratio of the initial concentration of COCl2 divided by K. We put those values in, so 1.5 divided by 2.2 times 10 to the minus 8. And what we end up getting is 68,181,818.1. And that's very, very much larger than 500. So if it's greater than 500, we're in good shape. If it's greater than 500, it's insignificant. It makes no difference to the 1.5. So what I'm going to do up here is say, all right, our millionaire, well, boy, he just lost a few more pennies. That's not going to hurt him. That's insignificant. Not going to miss it. Not going to make any difference to that 1.5. All right, we put our values in. Let's solve to find out what that X is. Here we go. We know what K is. K is 2.2 times 10 to the minus 8. Carbon monoxide is X. Chlorine is X. This is the initial concentration. And again, you notice how we got rid of the minus X here. And that makes this reaction a little bit easier. Okay, and here we go. We cross multiply. All right, because this is the same thing as saying there's a 1 there, so we'll cross multiply. X squared is equal to 2.2 times 10 to the minus 8 times 1.5. So there we go. And now we want to get the square root of our answer. And there we go. So the square root of this is 1.8 times 10 to the minus 4 moles per liter for carbon monoxide, which means it's going to be 1.82 times 10 to the minus 4 moles per liter for chlorine, because that's what X is. We just found X. And is this significant? Well, let's verify our assumption. Let's see if it is significant. Let's check it. 1.5 minus X. We do our little math here. 1.82 times 10 to the minus 4 works out to be 1.49998. Well, we only got 3 significant digits in the question because we started with 1.50. So when we round up for our digits of significance, the 9 again will round up to be 1. It didn't make any difference. This value here is insignificant compared to the 1.5. Yeah, we subtracted it, but it didn't make any difference when we looked at our significant digits. There we go. Okay, now I know this is fast, but you can fast forward, rewind, go back and look at them, try a couple problems. Don't forget, our online tutors are there. They can help you with some of these problems as well. And we have lots of online content that you can check out. Your textbook is a good resource too. Don't forget that. Lots of good examples in your textbook. And there we go. Okay, so check out your textbook, check out your online tutor, and if you have any questions, if you want me to do a couple more of these, tell me what questions you want me to do and drop them in the discussions, and I can do a recording for you. Okay, bye-bye.